I'll tell you this computer full. Yeah. Okay, good. So that was a nice story about how they came up with um, swords, right? This particular guy among the Pythagoreans who came up with that idea, right? So what we now that we're introduced to swords, um, we want to explore them a little, right? So we're going to explore swords a little. Yeah. I think I did a video one time where I chopped out all the little bits I tell you in stories and experiences and so. Because I never know what you'll do with it later on. So I chopped all of it out. So it's good I start recording now. Whoever missed the class would miss the story, right? You got to come to the class. It's not a it's not a correspondence course, right? It's not a fully online course. It's just for one, two people who's missing will have a recording. Okay, good. Yeah. So as we said, we talked about some examples of swords there, right? So let me give you a couple of examples. Root 3, root 2, I mentioned, right? Root 4, you wouldn't call it a sword, right? Because that's a nice wrong number 2, right? But a sword basically falls into the category of irrational numbers, right? Um, because they can't be written as an exact fraction where the numerator and denominator can be integers, right? Root 3, you just can't write it as a fraction with the denominator and the numerator being integers, right? Yeah. And if you were to try to maybe put them in a calculator, root 3, you see it's I think what you call a non-terminating decimal, right? Um, you'd find that with them, right? Good. And then you'll hear just to introduce some things you might hear about swords and so, right? You'll hear about what we call an entire sword, right? Um, what's an entire sword? Root 2, you call that an entire sword, right? Sword. And you'll have, let's say, 2 root 2, you call it a mixed sword, You have these names, and so some different textbooks would, they'll give you all kinds of things. Good. So let's explore swords a little, right? For example, let's try to write swords in their simplest form, right? So writing swords in their simplest form. Good. So let's take an example. You have something like this, root 28, right? Root 28. So what you want to do with a number like this, right? Um, you want to see if there's any perfect square that is a factor of that number. And then indeed there is, right? So you notice as 4 multiplied by 7 will give you 28, right? So what you can do, there's a rule that allows you to split this up. And I don't want to appeal to indices here, right? If you know a little bit of indices, you should. I know I'm going to indices afterwards. Like this means 4 by 7 to the half power, right? And this can rightly be written as 4 to the half times 7 to the half, right? So same thing here, right? So you can put square root of 4 by the square root of 7. And you know that the square root of 4 is not a sword. It's a nice number like 2. So you end up with 2 root 7, right? So writing root 28 in its simplest form, you get 2 root 7. Think you get that? look for a perfect square that is a factor of the number under the radical sign or the square root sign, right? Like, let me give you another example, maybe. Um, oh my, who's trying to call me now? Yeah, let's take another one. So you have, all right, the square root of 63. Wonder why this person is insisting. Let me see if it's somewhat something important. Yeah. So let's take another example, right? So this, you can see that, okay, there is a perfect square that's a factor of 63. I think it's 9, right? So you can write this as root 9 by root 7. So you have what? 3 root 7, right? Think you get it? And of course,
Yes, sir.
well, I don't have to tell you that, well, you can take this and write this back, right? You can see the process, right? You see the process of doing it the other way around. And I'll tell you what, it's good to know the process. The reason why both taking this and getting this, or taking this and getting that, right? You never know. And that's a funny thing, huh? Um, it's how the entire and all your courses are taught. We try to teach you everything, right? I mean, we can't teach you everything, but we try to teach you a little bit of everything. And let me put it that way. Because we never know what you'll need later on. Right? That's the thing. And that is why I just want to deviate just a little to tell you this. It is the reason why there is this group of people, right, who they were called um, post-modernist um, curriculum developers, right? And they're saying that, look, you see this thing where you're trying to teach children things and like no, I can't pick out a situation just like that where you will need to take this and get it in this form, right? I think in one of the worksheets there is a thing that you'll make use of this knowledge, right? Um, so sometimes you want to know, why am I being taught all this thing, think about your bio courses, your chemistry courses, all those little bits. And as I told you before, you go on a job and 99% of what you were taught, you don't have to use because the job doesn't require it. So there are these people who says, you know what? No. Why not let's teach by something called, there's some of them calling it project-based learning, right? Project-based learning, right? Some people talk about problem-based, right? Problem-based learning, right? And what they're saying is, look, let students or yeah, students find some a project, or they're given or they find a project, and that probably has to do with some problem that the community or the country or whatever is facing, right? Or it can be a project, it can be a problem, and let them try to solve it. And in the process of solving it, right? Um, they might very well have to learn a little bit of mathematics, a little bit of science, a little bit of, you know, all kinds of things, business, whatever areas they have to learn. But only that will help them to do this project, to carry out the project or solve the problem, right? So they see the need, they'll say, you know what, this thing is useful to do this project, or it's useful to solve this problem, right? Some people are arguing to go that way, you know. Um, as a matter of fact, I had an idea I was trying to throw to my fellow colleagues in the division, right? Where and I'm borrowing that idea from there's a doctor in Georgetown named Dr. Fox, right? I think she got an award for um, I think she came up with a process that nobody in the whole wide world knew about it before, right? And I think it had to do with some process to break down crude oil using something. I can't remember. She got some award for it, right? As a best woman scientist in the world, or I don't know where, right? But she has a foundation where students would, they come to her with ideas. Not her, I think there's a whole group of them. And I was trying to bring that idea to Borbies, where students would come to us with an idea, like the computer science boys would say, you know what, sir, I want to develop an app that will do this, or I want to develop a website that will do this, or the chemistry people say, you know what, I wanna, develop a process to do this. Or the bio people might say, you know what, I want to get into the conservation of something, or God knows what you'll come up with, right? Or you might say, look, I want to develop a processing a method for some kind of food that we are wasting a lot, and good. And what happens is that you're going to study this particular problem, right? Like right now we get in blackouts in this whole country. You want to think, well, can I propose? Can I propose? Some people are only fine during my class to be calling me, and some student having trouble in logging in and all that. Anyway, yeah, there's another one again calling me. Yeah. So yeah. Yeah. So what you do is you'd come to us and we'd probably assign you a mentor, you know, who would kind of help you with the project because they have some experience, some knowledge about it, right? And we could actually help you with maybe funding and so, right? Government help and all of that. So you never know by the end of the 4 years, right? When you come out of here, you have something that can be a side hustle for you. It could also be a major business, right? It could be something that can generate some income for you. Or you never know you're going to it full time, right? You never know you're going it full time, right? And of course, the lecturers who mentor you and so might very well want equity in the business, you know. So yes, sometimes you taught stuff that you want to know, what am I going to do with this, right? And that idea would have gotten you to be using at least a small fraction of your knowledge meaningfully, right? Meaningfully. All right, let's get back to this, right? So um, let's talk a little about um, maybe addition and subtraction of surds now. Let's go with addition and subtraction of surds. All right, good. So just like in algebra, right, where when you're dealing with, okay, 2x plus 3y plus let's go with 4x minus y. You can't add the x and the y's, right? You have to add the x and the x, and maybe you subtract the y from the the y. You can do that. Same thing with surds. If you have, let's say, okay, 2 root 3 plus 7 root 3, because they both have a common surd inside, right? You can add this and say, oh, you have 9 root 3, right? But if you have, let's say, all right, 8 root 3 plus 5 root 2, you can't do nothing else with it, right? Because they're different. The surd, there isn't a common surd there, right? With this one here, using your distributive law, you could very well do this. You factorize out root 3 and you get 2 plus 7, which gives you your 9, right? But you don't don't write root 3 9. Don't write that. You put a 9 in front, right? Put a 9 in front. Because sometimes some people just draw this line a little far and the 9 gets under the root and it's trouble, right? Think you're getting that so far? So the only way you can add and subtract surds, they must be what you call they must share a like surd in each term, right? So sometimes though, right? Sometimes you might have two surds that they don't look alike. They look like you can't add them, and so, but sometimes you can very well add them. Let me give you an example. You can have something like this: root 12 minus root 27. And maybe you have to somebody tell you to simplify. Simplify it. So you look at this and you say, no way. Surds that tells us that if these two things are different, you can't just subtract them, right? But what you could do is see if you can break down 12 and you can break down 27 to see if the two surds can actually have a common surd inside, right? So like 12, okay, you see it's 4 by 3, all right, minus, what's this one, 9 by 3. So we seem to be heading somewhere. You will get 2 root 3 minus 3 root 3. And yes, we have a common surd there, right? So we can now 2 minus 3 will give you minus 1 root 3. See? So you could simplify it, right? So don't conclude as soon as you watch this, oh, they're different, we can't subtract them. No, don't say that. See if you can simplify it. It may work, it may not work, but you just have to, you may just have to see if you can simplify it, right? I lost my course. Good. So let's go to multiplication now. Multiplication of surds, right? And like again, if you have x by y, you can multiply them, right? Regardless, whether they're different, you still can multiply them. The same is true of surds, right? Like you get root 2 by root 2, you can multiply them, right? You get root 2 by 2, which is equal to root 4, which is 2, right? Understand? Root 5 by root 5 is the same as root 5 times 5, which is root 25, equal 5. You can multiply them, right? Very much like when you were dealing with adding and subtracting algebraic terms and expressions, when you were multiplying and dividing, and so very similar, right? Let me do one that it's not so plain like this, right? Maybe it's a little more complicated. Let me go back to, let's say you have something like this, all right? Root 8 multiplied by root 10, right? So what can you do with that? So let's say, all right, you have what? That would be root 80, right? And you can now see if you can simplify that, right? And you can see, I want to think that is equal to 16 by 5, right? 6 is, so yeah, 80, yeah, right? And this here is a perfect square, so that will be root 16 by root 5, which will turn out to be 4 root 5. All right, let's take a final example on multiplication. Tell me if I'm going too fast or what, So let's see. Okay, 2.
No, sorry, going good with this
three.
topic.
Yeah, this is an easy thing, I would think, right? So you have something like this, right? So you get what? 2 times 3 is 6, and you get root 3 by 2, so you get 6, root 6, right? Yeah. Ugly as it is, well, that's what you get. What you do? Can't do nothing more. Let's try another one. Look at this one. 2 root 12 by 3 root 8, right? So you get what? That's 6 root 12 by 8. You get what? 6, 96? I hope my tables beating me up here. Yeah, right? Which is also equal to, um, it's 16 by 6, right? This is 36, yeah. So this now, this part here, okay, let me go up here. You get 6 root 16 by root 6. This is going to be 4, right? So 6 by 4 by root 6, right? So you get 24 root 6. Follow it?
Yes, sir.
Yes, sir.
Let's get something a little harder. Um, Here's something harder. Let's go with something like this. Root 5 bracket root 6 plus root 7. Now you have to maybe simplify. Oh my, what happened here? Simplify. Right? Something like this. Right? So you use your simple what do you call the thing? Distributive law, right? And you simply multiply this by everything in here, right? So you'll get root 5 by root 6 plus root 5 by root 7, right? And you'll get what? I don't think you can simplify this for them. Minor plus, huh? Plus root 35. I don't think that there are any factors of 30 or 35 that's a perfect square. So you might have to just leave that the way it is, right? I'm hoping that, well, maybe in another one, this wasn't well thought of. Maybe that this you could have simplified a little more, and that you could have simplified a little more, you know? Yeah, maybe you'll see one like that someday. Take this off. Let me go again. A good one to know is like if you have, let me show you this one. Root 8 plus root 3 times root 8 minus root 3. Anybody can think what that will turn out to be? We just finished quadratics, right? So, yes, the money.
Yeah, sir, it will be root 68. I mean 64. Root 64. 8 threes is root 26. And
Can you
yeah,
recognize this to be a plus b multiplied by a minus b, which is a
Perfect
square
square.
minus b square, right? I'll just do quadratics, you know. So you gotta watch it good. So
oh,
basically, it's going to be what? 8 minus 3, huh? Which is 5. Is that right?
I didn't thought about doing it like this.
Yeah.
Like I'm just so used to when I see it like this, just expanding it. I didn't thought about
Yes.
like
Yes. Well, that's the thing, right? Sometimes the first thing that comes to your mind is use the brute force and ignorance, you know, that we have in us. Work the thing out and multiply everything out and so. But if you know, if you can remember like these things and say, well, okay, you know what, this thing has some resemblance to something I saw before, you know, and that's where you working in the area, you become familiar with these things and so, right? Good. We talked about then what? Surds, addition, subtraction. We talked about multiplication. We didn't mention division yet, right? Division, right? So let's see. Instead of division, you're going to see a lot. You're going to see this term, rationalizing, rationalizing the denominator, right? You see that, right? Rationalizing. What they're talking about here. Let's take an example. Right? Let's take an example. Say somebody tell you to rationalize uh, the denominator of uh, 3 over 2 root 7, you know, something like that. So what I'm really telling you is that, okay, um, they don't want this rational number, this irrational number in the denominator. They want to get it out of here, right? They want to get it out of here. So, and for those who are into, I think the computer science boys should be able to comment here. If they were to program a calculator to do something like this, it is better if this square root is in the numerator, right? I've heard that from programmers saying that the code is simpler to write if this here is in the numerator. So what you do, you want to rationalize. You don't want a denominator to have a square root inside. Any square root must be dealt with in the numerator, right? Especially the older calculators and so, it's harder to do something like this, right? It's harder to do something like this. But if you find a square root of something and then the answer you get, then you divide by maybe 2 multiplied by 3. That's easier. But to put in a square root sign in the denominator of a fraction, very, very difficult, right? I know we have come so far forward that is not the case now. You can write stuff the way it is, and the calculator is going to do it, right? Maybe you can try it as we're doing the problem. Anyway, what we mean now is we have to get this radical sign out of the denominator. So there is a technique where you multiply the numerator and the denominator by root 7, right? And what would happen? Well, it's like you multiply by 1 here, right? Root 7 over root 7 is 1. So you end up with 3 root 7, and root 7 by root 7 becomes 7, and that 2 becomes 14. And there you have it, right? You got 3 root 7 over 14 is the same as 3 over 2 root 7, right? Same girl, but she just arranged her hair and makeup and, you know, whatever else differently. And for those of you who are, well, I don't think any of you are old enough to know Very long ago calculator, this was a hard thing to put in. This was a hard thing, right? But long ago calculator, what you'll do, you find the square root of 7, you press equal, it's going to give you a horrible decimal. You take that decimal, multiply it by 3, and the answer you get, you press equal again, and then you divide by 14, right? But as I said, to do this with a long ago calculator was very difficult. You take 3 divided by, right, 2 times root 7, and this root 7 wasn't easy to insert because you never used to put in root 7. You used to press 7 and then the square root, and then you have to remember you have to put a bracket here, right? You have to put a bracket, and that does create a lot of problems with students, right? So it didn't lend itself to the kind of calculators that we had in those times, right? So this here was nice. You could feed this in a calculator very easy. Let's do maybe a harder one. Let's do a harder one that involves let's see if I can find a one that is a little. All right, watch this one. And my intention here is not to exhaust all the possibilities, right? In your tutorial, we're going to do a lot more. Look at this one. You have 3 minus root 5 over 1 plus 3 root 5. So let's say you have to rationalize that denominator. So this is what you do. You make use of that same thing that we had, that a plus b times a minus b is equals to a squared minus b squared, right? So we're going to do that here. We're going to multiply the denominator by what we call the conjugate of 1 plus 3 root 5. So you get 1 minus 3 root 5 over 1 minus 3 root 5. Right? And what will happen? When you multiply the numerator, you'll have something ugly, but when you multiply the denominator here, right, this is what you'll get. I mean, move it up a little bit, just for some space, right? So you'll get this. You'll do the multiplication, right? I'll skip that out. I'll multiply this by this. You know how to do that, right? It's like two binomials you're multiplying. I'll skip that. And you'll get something on top there, right? Skip that out. But at the bottom here, you're going to have 1 square minus 3 root 5 square, right? Which will work out to be, well, you will work out the numerator. But at the bottom here, you will end up with 1 minus 3 root 5 square give you 9 by 5. Would that be right? 3 square, yeah. Yeah, that's correct there, right? This 3 will go over, yes. So you will end up with something over, what will this be?
45.
45? So 1 minus 45, right? Will give you minus 44. Anybody worked out what the numerator will be? Anybody worked out the numerator? Take a second and do it. Tell me what you do.
So, sir, negative 9 plus 5 root 5.
in the numerator?
Yeah.
I have 18 minus 10 root 5.
Because you have 18 minus,
Minus 10 root 5.
yeah, that sounds more like it, right? So we end up with, let me shift this whole thing aside. See if we can, yeah. So I'll have, who write this all this craziness here? Remove it, boy. So we have 18 minus 10 root 5 over minus 44. So what we could do, if I take out, what's a common factor here? 2. Watch this. If I take out minus 2, right? I'll get 9, sorry, minus 9 plus, plus 5 root 5, right? Oh gosh, give me a second. Hi, yeah. Yes, you are coming? Answer McCall. Yes, yeah. Like, yes, the yellow house on the right. Yes. Yes. Yeah, sorry about that. Yeah. So all of this over minus 44. So I think you could cancel this here. Right there, and you get you get 22 here, right? And then you wouldn't write this so ugly. You would write 5 root 5 minus 9, right? Don't have a minus sign sticking out here over 22. Right? So it's a little harder. But doable. Good. So can I move this?
Sir, can you explain one more time how you got the perfect square?
Which one? Where is the perfect square? Where?
A plus B, A minus B equals A squared.
Here? Down here?
Yes, sir.
Yeah, it's just a technique. Mathematicians came up with that to get rid of this radical sign here, this root 5. We don't want that here. So what we do, again, it must puzzle you. Where did we come up with the idea, right? So, that's what mathematicians do. They find ways of, simplifying these things. Somebody came up with the idea that, let's multiply this whole fraction by what we call, they give it a name, the conjugate of this, right? So instead of 1 plus 3 root 5, we use 1 minus 3 root 5, right? So 1 minus 3 root 5 over 1 minus 3 root 5 is like you multiply by 1, right? It's a trick, again, we use in mathematics to accomplish some purpose, right? We take this over this, but the reason why we're doing it is what will happen when you multiply here by here. Because when you watch this thing, you're seeing something like what? You see A plus B, A minus B. Do you see? You see this one? A is like 1, B is like 3 root 5. A is like 1, B is like 3 root 5. It resembles this thing here, right? Therefore, you don't have to go and do the long multiplication. You can know that, well, this here is equivalent to that. And that's why I'm telling you, I didn't bother with the numerator. Somebody else did it, thankfully. But the denominator is going to work out to be this. Right? The square of the 1 and the square of this here. Right? 1 minus the other. Difference of squares. It's a deliberate act, you know, and it works. It works.
Yes, sir, I understand.
Yeah, take some time to internalize it. You know, what is it that these people are doing here? You know, in the tutorial, you'll have plenty more to play around with, right? Your lecturer, your tutorial tutor is going to spend some more time on them. Give me a second. I just want to learn these people about something. Good. So I want to move away from this. And my intention is to get to logarithms in the second half of this class. But I'll just throw up back here the laws of indices for you. Laws of indices. I think you have done sufficient of this at your CXC level, you know. Let me use, okay. You have p to the x plus, times p to the y. You know that that's p to the x plus y. You have p to the x divided by p to the y. It's equal to p to the x minus y. I guess you know all of this, right? P to the x raised to the y power is the same as p to the xy power, right? I think there's another one like this, the square root of p to the x, or not square root, let's say the y root of p to the x is equals to p to the x over y. I think you all should know these rules from CXC, right? There's a, it's not a new rule, it's really a, what we call a corollary. You know, it came from the other rules that p to the 0 is equals to 1, right? And p, if p is a non-zero number, right, that is. And I think there's another one, 1 over p to the x is the same as p to the minus x, right? These are, they're not new rules. These two here, they're not new rules. They came from these over here, right? They came from these over there. Good. So with that little, you know, review of indices, I'm not going to do examples, and so there are going to be plenty in the tutorial for you to refresh your memory and impress your tutorial tutor, right? What I want to go to is something new. Do you want a little break before we go on? Do you want a little break? Let's take a 5, huh? Let's come back at 4:25, 10 minutes.
Yes, sir.
Yes, sir.
Yeah, remind me to add another percent for you know, helping me out. You're assisting me in this class. Very good. You're looking out for me, boy. That is what I want. And you're looking out for everybody who will have to look back at this video to learn something, or those who missed the class. I should take 1% from them and give it to you.
So I
That sound
just
good? That sound good?
watched the video. Yeah, yes, sir. I just watched the
Okay.
video back.
Great, great. Yes. Good. So what's logarithms really? It's basically another word for exponent, or it's another way of writing exponents, right? Let me give you, to show you what I'm talking about. So if you have, all right, b to the n equal to x, let's say you have that, and you're familiar with this. Raise a number with a base, well, the base is b, to n power, and you get a number x. You're familiar with that. That's what you've been doing all the years in high school. What logarithms is about is writing that same thing, but in an inflected way, right? And let me show you what it is. So you can write the logarithm of x with a base of b is equals to n. So it's the same thing, but you're just saying it differently. I guess you're all doing English 1105, and you no doubt will talk about inflection, right? You say the same thing, but you're saying differently, right? A lot of you are using AI in your work, so you say, here, what happened? Miss could pick up this thing as AI, right? So you take the thing and you probably put it in another what you call a paraphrasing tool, and the thing says the same thing, but just says it differently using synonyms and whatever else, changing up the structure of the sentences and so, right? And some of these paraphrasing tool, I remember at one time I actually paid for one, trying to remember what its name, not Grammarly, I forgot this one. And it was when it rewrites something, it used to write it like a real, it was like a lay person, you know. It was too down to earth, like it doesn't sound scholarly, right? I had to discard it. I can't pay $15 a month for that crap, right? It made me, you know, sound unintelligent and you know, I got rid of it. Yeah, but back to this, right? So you're used to saying it like this: b raised to the power n equal to x, right? In logarithms, you say the logarithm of x with a base of b is n, right? So again, as I said, logarithm is another way of highlighting the power of the number, right? And which is what? The logarithm of x is n, right? It's just that you're sticking this b in here because you want to tell the reader that the base that you had before was b, right? Because that's what you have here. B raised to the power n equal x. Written another way, the logarithm of x with a base of b is n. Just an inflection, right? Just to give you some examples and so. Like if you have, okay, the logarithm of 32 with a base of 2 is equals to 5. And you know this, right? That 2 to the 5 equal 32, right? Oh, I think so, yeah. Right? So I'm just writing it in logarithmic form. Right? Like, okay, let me give another example. All right. Let's go the other way. 4 to the minus 2 equal to 1 over 16. Right? So how can you write that in logarithmic form? So you'll say the logarithm of 1 over 16 with a base of 4 is equals to minus 2. Right? Saying the same thing. Think you're getting the knack of it?
Yes, sir.
Yes, sir.
Let's take one that will tickle your brain a little. The logarithm of 1 with a base of 8 equals 0. Tell me if you figure that to be true. In other words, I'm saying 8 to the 0 equal 1. As a matter of fact, the base isn't even important there. The base can be any non-zero number, right? And when there's something that is true, when something is true for any base, sometimes they just put the logarithm of 1 equals 0. They don't even put a base here, right? Well, with the exception of, well, the base can't be 0. Those who are into logarithms and so would know that, you know what, and indices, you can't have 0 to the 0 power equal 1, right? That is not correct. Any non-zero number to the 0 power is 1, right? So there's a general thing that the logarithm of 1 with any base is equal to 0. And remember, b must not be 0, right? B must not be 0. Just keep that in mind, right? Some other little things you would pick up as you fool around with logarithms is like, okay, you know that 5 to the 1 power equals 5, right? So the logarithm of 5 with a base of 5 will be 1, right? So generally you can say the logarithm of b, the base is b, is 1. Get it? Good. Let's take another one. Let's say, okay, the logarithm of 2 to the m with a base of 2 will be how much? Is going to be m, right? In other words, you're saying, what do you have to raise 2 to, right, to give you 2 to the m? M, right? So again, you can come up with a general rule. The logarithm of b to the x with a base of b is equals to x. Well, let's evaluate some logarithms that can be tricky sometimes. Let's say you want to evaluate log of 1/9 with a base of 3. So what are you going to raise 3 to give you 1/9? But you can recognize that to be, okay, like, okay, 3 to the minus 2 equal 1/9, right? So the logarithm of 1/9 with a base of 3 is going to be minus 2. I think I did an example like that before, right? Similar to that, which I think is 1/16 with a base of 4. I think we got that, right? And there are lots and lots of little, tricks and so that you will pick up as you read more on logarithms, right? There's no harm in picking up a textbook, right? And read a little about logarithms and examples in the textbook. I can't tell you everything. I can't tell you everything. Nobody can tell you everything. Even the textbook you read, you go on YouTube and you watch a few logarithm videos, sometimes you don't pick up everything, right? Good. What I want to highlight to you now, that, okay, we're having logarithms and you notice we're highlighting, okay, the base, right? Logarithm with a base of b. And you see sometimes we use 2, we use 3. Y'all give me a second. Okay, yeah. So you notice we're talking about the base 3 and base of 2 and base of 8 and all of that, right? So what mathematicians realize is that, well, if we were to make a calculator, right? Or those times we hadn't calculators, we had what you call tables, right? So they said, look, we can't make tables for every single base out there. So what we're going to do is we are going to try to write all numbers, right? We're going to try to write numbers with a base of a single number, right? And they came up with, you know what? Since we're dealing with a base 10 system, they came up with something called common logarithms, right? I left out the R. Yeah. Common logarithms. And common logarithms has a base of 10. right? So what they started to do is they started to write every number in terms of a base of 10, right? And they actually make up tables. Long ago, when you write CXC, people didn't have scientific calculators like today. They used to share out. They used to share out what you call 3-figure, and later on somebody did four decimal places, and they call them 4-figure tables, right? So when the exam started, the invigilator would come around and share a 3-figure or a 4-figure table to you, right? Most people had adding machines. Lots of people write CXC without the adding machine, right? They'd actually compute everything by hand, right? Those who write GC and so no calculators, they hadn't, people couldn't own one, right? So they had 3-figure and 4-figure table. But the whole idea I'm trying to tell you is that you try to write all the numbers now, right? You write all the numbers with a base of 10. So like, okay, just to give you this, let's say, okay, 1 over 1,000 is really 10 to the minus 3, right? So the logarithm is minus 3. The logarithm, and when you're dealing with base 10, you see the textbook would write it like this: LG of 1 over 1,000. They wouldn't put 10 here. You have to know that we're working in base 10, equal to minus 3. The logarithm of 1 over 100 is minus 2. The logarithm of 1 over 10, right, is minus 1. You know, the logarithm of 1 is 0, and you know the logarithm of, the logarithm of 10 is going to be 1. The logarithm of 10 is going to be 1. The logarithm of 100 is going to be 2. You know, they're not going to put the base because it's understood that you're working in base 10. And I think all the scientific calculators of today would have what we call common logarithms, right? Our entire system was designed so that we can use common logarithms in all the sciences, right? It's a very common base, right? Later on, they came up with something called the Napierian logarithm. Napierian. Maybe you can do some research on why they call it this logarithm, right? And that base is E, right? Somebody punch E into their calculator, E to the 1 power, and see what it is. They found this number E to be occurring naturally in nature then, right? For example, I think those of you who did what you call it, chemistry, physics, and so, and when atoms decay, there is a formula like this. I don't know if you ever see this. I don't think, maybe not, right? So, okay, sorry, this is not N naught, this is N, right? The number of atoms that will be left behind, right, is equals to how much you start with times E to the minus KT, and K is what we call the decay constant, right? And time is the time in years, maybe, right? So this E, this number E, occurs naturally in nature, right? There are a lot of formulas in the sciences, especially physics, where E will show up, right? And they want to know where did this number come. It's occurring naturally in nature, right? Maybe you can Google it, right? And maybe tell me the next time we catch up about the number E and where it is that they discovered that E is occurring naturally in nature, right? And when they found this number, anybody punch it in their calculator, E to the 1 power is how much?
It's 2.71828181828.
Yeah, it goes on, right? It's an irrational number, just like pi, right? Just like how pi also is a naturally occurring number. They see it all over in nature. E shows itself up, right? E showed itself up just like that. And a lot of physics formulas would have E or feature E inside, right? And then because of that, you will see something on your calculator. You'll see e to the power x, and you will see ln, ln or ln x on calculators. I don't know if you have a calculator nearby. Watch it, you'll see that, right? It's a Neperian logarithm, ln x, right? Again, if you're finding, you don't write log of a number, let's say 2, with a base of e. You don't write that. You say the ln of 2, right? And you can punch it in your calculator and see what it is. In other words, if you raise e to that power, it's going to be equal to 2. Right? So later on, they found out about a Neperian logarithm. And they also have, well, you don't find tables with the Neperian logarithm or the, what you call the natural logarithm. You're going to find calculators built with it. Because by the time they really adopted Neperian logarithm into the sciences, well, calculators start to show up, you know? Good. So now that we talked about, you know, these bases that they make, they're built into calculators and tables and so on. They have what you call the laws of logarithms, right? The laws of logarithms. And they're very similar to the laws of indices, right? That the log of the product of two numbers, and okay, you don't have to have a base. Well, let me put a base. Is equals to the log of one of the numbers with that base plus the log of the next number with that base, right? And remember that thing? That if you were to multiply two numbers, right? Raise to some power, you would add the powers, right? And that's what's happening here. So the logarithm of xy is the same as the logarithm of x plus the logarithm of y, right? I am not going to call the base. And similarly, the logarithm of x over y is going to be equal to the logarithm of x minus the logarithm of y, right? And again, you remember that. When you are dividing, right, x raised to some power by y raised to some power, you usually subtract the indices, right? That's what's happening here. Right? The logarithm of x is a power. The logarithm of y is a power. So you subtract the powers. This is an interesting one. It came, oh, let me write it right here. The logarithm of x to the power n, all right, we'll give it a base too, is equals to n log x, right? So if you were to find the logarithm of a number raised to a power, it's the same as the logarithm of the number multiplied by this that power n, right? And let me go back to, if you were to write this differently, what will you write? You write b, right? So some number, let's say z is equals to x to the n, right? So in other words, z is really this power, right, times the logarithm of x. And that's what they're writing here. That's what they're writing, right? Another way of writing it. Let's apply the laws. Let's apply the laws. Maybe I'll put the questions right here. Let's put it right here. I will do the examples here, right? Let's apply them to some. Let's say you, and I'll kind of combine some of the laws for brevity, you know, not too many, too simple examples. Like, okay, you want to maybe expand the logarithm, and I'm not going to stipulate a base, right? We're assuming the base is some number. A, B, C square over D cube. Want to expand that, right? So you can write this as, okay, it's equal to the logarithm of ABC squared minus the logarithm of D cube. Now this here can be expanded further. That would be equivalent to the logarithm of A plus the logarithm of B plus the logarithm of C squared minus the logarithm of D cube. Then in your next step, well, you can't do much with this one. Can't do much with that one. But here you can put 2 log C minus 3 log D. Right? So there you use the laws of logarithm to expand out this whole thing. So you apply, I think, all the laws in one here, right? In a single example. All 3 laws one time. There is a very valuable tool that you will use in the solution of equations that involve the exponent, where the unknown is in the exponent. And later on, when you do calculus, it's going to be a very valuable tool. And that has to do with what we call change of base of a logarithm. Right? How do you do that? So let me illustrate with an example. If you have the logarithm of x with a base of b, but maybe you don't have a calculator that has base b. You want to change it to maybe base 10 or base e. Well, this is the formula for it. The logarithm of x with a base of a, because you're changing the base to a, over the logarithm of b with a base of a. And this is a valuable formula, very valuable formula, right? Where you can change the base. All right, I'll show you an example in just a moment where you need the change of base. So keep that in mind. Maybe let's throw an example here. So let's say, all right, you want to evaluate something like this, right? You want to evaluate the logarithm of, well, not 8. Let me not use 8. Let me use a number that it's not easy, right? So let's say the logarithm of 6 with a base of 2. You can't know that unless you have a specialized calculator, right? You don't have a calculator that will give you the logarithm of 6 with a base of 2. What you can do then is change the base. And what you can do is find the logarithm of 6 with a base of 10, because the calculator will do that, over the logarithm of 2 with a base of 10. The calculator will give you this, the calculator will give you that. Just find log 6, divide by log 2, and you will get your answer. I don't know what it is, but I'm just showing you how useful change of base is. And you'll keep this formula. You will need it when you have to solve certain types of equations, and more so in calculus. So now that we have logarithms, we can now be able to solve what we call exponential equations. Right? In high school, you used to do something like this. 2 to the x equal 8. What is x? You have to solve something like this, right? And you know that, okay, 2 to the x, 8 can be written as 2 cubed, right? So x then equal to 3. Easy, right? But what about if you have something like this now? Solve 5 to the x equal 10. You can write 10 as a power of 5? No. So what you do then is you can find the logarithm of both sides. The logarithm of 5 to the x equal to the logarithm of 10. Because when I use LG, remember, I mean base 10, right? So I'm not going to write LOG with a 10 at the bottom. LG means you're working in base 10, right? You're using what we call common logarithms, right? So what do we do here? So we find a logarithm of both sides. You know there is a rule where you can bring this x to the front. So you have x log 5 equal log 10. Therefore, x then is equals to log 10 over log 5. And that's some number. I think punch it in your calculator. It should be 1.43 or something like that. To 3 significant figures. Anybody get the 1.43? Or I lost you there?
Yes, sir, I get it.
Good. You just log both sides, right?
No, sir.
You're not getting the 1.4. Log 10 over log 5. You're not getting it? Log 10 over log 5. I think you can do ln 10 over ln 5 too. You probably don't
Yes,
know
sir,
how
I
to
got
use
it.
your calculator. You need some practice. I look at another one. So you have, okay, all right. You have to solve log. And I think when they don't have a logarithm there, I think they should have a base. All right. Let's go with a base. Let's go with a base. All right. Let me do another one. Let me do another. Look at this one. 2 to the 2x plus 3 bracket 2 to the x minus 4 equals 0. Look at this one. You have to solve something like that. Now, if you look at this thing carefully, this thing looks like a quadratic. It has the form of a quadratic. You can write this 2 to the 2x as 2 to the x square, right? Let me see. 2 to the, yeah, could you write it like that? Square plus, okay, 3 to the 2x minus 4 equals 0. You agree with me? I can write this as that using your laws of indices in a reverse fashion. And what you can do now, you can let 2 to the x be equal to a big X. So your equation becomes x squared plus 3x minus 4 equals 0, right? And I think you can factorize that as x plus 4, x minus 1 equals 0, right? And then, okay, either x plus 4, okay, that's a bold x, a big X we have, equals 0, which implies that x equal minus 4, or x minus 1 equals 0, which implies that x equal 1, right? So we're not done there. We're not done there. Let me make it a little smaller because I need a space. right? So look here, if you have, okay, remember x, remember, I'm gonna write out the word, remember x equal 2 to the x, right? So we can write back 2 to the x equal minus 4. Now, if you were to try this, if you were to try solving this, let's do it and see. The logarithm, and you're using base 10 now, right? 2 to the x equal to the logarithm of minus 4. So you have x log 2 equal log of minus 4. X then is equals to log of minus 4 over log 2. Now, if you were to try this and you punch it in your calculator, do that and see what happens. Press log of minus 4 and tell me what happens.
Sorry, it says error 2.
Error. The reason why is that, let me just give you a little bit here, right? The reason why is that the exponential function, let's say it's there, 10 to the x, that's what it looks like. And the logarithmic function is this here, logarithm of x, right? This line here is the line y equal x, right? The logarithmic function does not exist over on the negative side here, right? So you can't have the logarithm of a negative number, right? The logarithmic function, you can only find the logarithm of a positive number then, right? You can't even find the logarithm of 0. Get that? So that is why this one here is going to churn out an invalid solution, right? But on the other hand, I think there is a solution here, x equal 1. So maybe we can take that. So 2 to the x then is equals to 1, right? And you know you can write that as, okay, you don't have to do the whole logarithm bit. 1 can be written as 2 to the 0 power, right? So if 2 to the x equal to 2 to the 0, then x equals 0. And that's the solution to your equation. Right? So you're going to have a lot of practice in your tutorials. The notes I sent you will have more examples, and so you're going to watch those. You're going to have maybe your colleagues are going to present their solution of a couple in the tutorial sessions and so, right? So you're going to have a lot of practice. Good. So we're going to stop there with logarithms. And we have to discuss test number 1 or date for test number 1. So where are you when you're doing tutorials now? Where are you?
I'm at home, sir.
No, I mean, yeah, thanks for the humor. Are you at quadratics now in your tutorial sessions?
Yes, sir.
Good. So I guess maybe next week you're going to do this here, logarithms and indices and what else we did today, surds and so. So maybe the following week we can have our test, the 5th of November. I hope that's not some kind of holiday.
Excuse me, sir.
Uh,
The tests will be based on everything we did so far.
yeah.
Okay, in person.
Yeah.
Okay.
Right. So I'll give you that time to catch up yourself, and so the 5th of November will be your test 1, right? Good. So
Thanks, sir. Excuse me.
yeah.
The computer science people will be I'll be leaving now because we have
Yeah,
another class.
yes. We're done.